Welcome back, everyone. In this video, we will be concluding the section on L'Hopital's rule or indeterminate forms. Now, number 6 here will actually kind of have both of the final two examples in it. It's going to have the exponential indeterminate form, and as you go through it and you solve that, you actually, in an intermediate step, get the product form, which would be infinity times 0. But I want to go ahead first and just remind you of the other indeterminate forms. So products we haven't talked about, 0 times infinity. We'll see that in this problem, but I also have another problem to do. And then the exponential forms are 0 to the 0, infinity to the 0, and 1 to the infinity. Now, I very briefly wanted to explain why 0 to the 0, infinity to the 0 work like that. Well, the main idea is when you have an exponent raised to the 0, it's always 1, and that's because you can think of 0 being something like 1 minus 1. You don't have to actually think about it like that. It could just be 2 minus 2, 3 minus 3, whatever. But if you rethink at the exponent 0 as 1 minus 1 here, you have 0 to the 1 minus 1. Well, if you split it up using exponent rules, meaning you break it apart, you get 0 to the 1 times 0 to the negative 1. And then when we get rid of negative exponents, it comes to the bottom as a positive exponent. So this would be 0 to the 1 over 0 to the 1. Now, normally, when we see sort of exponents like this, our brain automatically wants to cancel them out, but 0 to the 1 is just 0. So it's actually 0 over 0. And this goes for any number. I could have done 2 here. 0 squared over 0 squared is still 0 over 0, and so on. And the same idea works for infinity. Infinity to the 0 is infinity to the 1 minus 1. And you just go through and do the same thing with infinity. And you end up with infinity over infinity. And the same reason why 0 and infinity work is it doesn't matter what the exponent is. You could have 2 minus 2, you could have 100 minus 100. When you get down here, you would have infinity to the 100 over infinity to the 100, and that's still infinity over infinity. So this isn't going to give necessarily an indication of how we solve them, but why these two are indeterminate forms. Now, 1 to the infinity is much more challenging on the face of it. And the way we actually figure that out, that this is actually an indeterminate form, is this way we'll go through when we solve our problems. So I'm kind of previewing what we're going to have here, but we're going to see that our problem is going to have 1 to the infinity. And when we have 1 to the infinity, it is an indeterminate form. And we'll see the method of simplifying to get it to 0 over 0 or infinity over infinity. But first, let's not take my word for it. Let's go ahead and do it. We got to plug in infinity. When we do that, 1 over infinity is 0. So 1 plus 0 is 1 inside. And then the exponent is just x, which means this is just infinity. It is exactly 1 to the infinity. And this is indeterminate form. In general, we know that means that this could still be anything at all. Now, one thing is that we have to convert it to 0 over 0 or infinity over infinity. Plus or minus, we know that doesn't really matter too much. We have to convert it that way. Well, what's the actual way to do that? So this is kind of the way I learned it, and it's pretty much the standard way. There might be some very, very, very subtle differences, but what you do here is you set something like y equal to the thing you're taking the limit of, which is 1 plus 1 over x to the x power. So you set y equal to the part of the limit, the entire thing, but not the limit included. Now, some people will say just have y be the entire thing, which is also fine. What we're going to do works, but I just find it easier to worry about the limit at the end. Right? So we do that, and then here's kind of the trick. You take this and you do the natural log of each side. The main thing that's causing our indeterminate form not to be a fraction is this exponent. And we can get rid of exponents by doing the natural log because we know it allows us to bring it down. So we get the natural log of y equals the natural log of 1 plus 1 over x to the x. And our log rule allows us to take this x on the exponent and bring it in front. So we've got the natural log of y equals x times the natural log of 1 plus 1 over x. All right, so we've got that. We've gotten rid of the exponent. We don't have a fraction yet, but I want to go ahead and just pause for a second and think about what if we tried to do the limit here. So now we want to try to do the limit. Let me actually write it an arrow from here. We want to try to do the limit as x goes to infinity of each side. Now it doesn't make necessarily a lot of sense when we say do the limit as x goes to infinity of the natural log of y, because y is representing this. It's just a placeholder to actually allow us to do the natural log of each side. If we just kind of said, take this and do the natural log, you're not really doing something proper. So we have to have an equation by setting the y equal to that part and then do the natural log of each side. And then this equals the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. Well, the thing about this is a product, so we can do the limit of each part. So this is the limit as x goes to infinity of x times the limit as x goes to infinity of 1 plus, oh, sorry, forgot to write the natural log. The natural log of 1 plus 1 over x. Well, the first part is infinity. Limit as x goes to infinity of x is infinity. And the limit as x goes to infinity of this, well, the inside becomes 1 because 1 over x, the limit would be 0, plus 1 is 1, and the natural log of 1 is 0. And this is our other indeterminate form. This is our product indeterminate form. All right, so how are we going to take care of a product indeterminate form? Well, the main thing to do is you have infinity times 0. If you bring something to the bottom, then it becomes reversed. And that's because 1 over 0 equals infinity and 1 over infinity equals 0. I'm going to erase this, but the idea is going to come from here. If you have infinity on the top, you can bring it to the bottom and make it 1 over infinity, which is 0. Or if you have 0 on the top, you can bring it to the bottom and make it 1 over 0, which is infinity. Right, so that's where this is going to stem from, but to avoid confusion, I don't want to actually have that written in. What you want to do is take this part and bring it to the bottom, because it's an indeterminate form, but it's not one where L'Hopital's rule works yet. All right, now what do I mean by bring it to the bottom? Well, this part here, the limit as x goes to infinity of the natural log of x, or natural log of 1 plus 1 over x, is staying there. So we got the limit as x goes to infinity of the natural log of 1 plus 1 over x, and we divide that. Now when we bring it to the bottom, it doesn't stay just x, because what happens when we bring something from the bottom to the top or top to the bottom is we have to change the sign of the exponent. This is really x to the 1, so it becomes x to the negative 1. So we brought this to the bottom, and just to make up for doing that, we have to change the sign on the exponent. Well, now what happens here, and it might help to rewrite x to the negative 1 as 1 over x, or you can just remember that when you have the limit as x goes to infinity of x to a negative power, it is 0. So this is 0, and on top, this is the same limit from before that gave us 0 originally. So at this point, we actually have it in a correct form where we can use L'Hopital's rule, because we have 0 over 0. Right, so just to summarize at this point, this is how you always take an indeterminate form that's an exponent. Not always, there can be other ways, but this will always work. You can always take them and set it equal to y, do the natural log of each side, and then when you do that, you should get 0 times infinity, one way or another, like we did here, and then you bring one part to the bottom. And I chose to bring this to the bottom instead of this because raising this to the negative 1 power with the natural log stuff is very messy, and we know we have to do the derivative. So I do the simpler thing, bring the simpler thing to the bottom. All right, so I'm going to kind of just write where we are at this point is from here. We have, keep in mind, this was always equal to what we have here. The limit as x goes to infinity of the natural log of y. We just had a whole bunch of equal signs, so it's still equal. It's equal to the limit as x goes to infinity. Well, I'm going to go ahead and just kind of write this as one limit. The top part here is the natural log of 1 plus 1 over x over x to the negative 1. So I'm just taking this last step here where we know we're going to use L'Hopital's rule on. But instead of writing the limit of the top over the limit of the bottom, I can just write it as the limit out front because I can distribute the limit in a fraction. All right, but we know this gives us 0 over 0 now, which means we can do L'Hopital's rule. This is 0 over 0 form. All right, well, L'Hopital's rule, now that we're here, we can almost kind of give ourselves some slight amnesia and say, you know what? I don't need to remember exactly what we started with yet. I just need to focus on this part. Well, the derivative of the top of this is not very fun, but we got to do it. So it's 1 over the inside, 1 over 1 plus 1 over x. Now you can simplify this beforehand, but when you do the chain rule part, when you multiply by the derivative of the inside, it's easier if you leave it like this. And the derivative of 1 over x, kind of write this on the side here. You might have this memorized, but the derivative of 1 over x is the derivative of x to the negative 1. You bring the 1 down, sorry, negative 1 down, and you subtract 1, x, negative 1 x to the negative 2. And then when you make it a positive exponent, it's negative 1 over x squared. So the derivative of 1, which is 0, plus 1 over x squared is negative 1 over x squared. Now, one thing you'll notice is that the derivative of x to the negative 1, when we do the derivative of the bottom, is the same exact thing. So we actually can just write it over negative 1 over x squared again. Right, this one came from the chain rule, doing the derivative of the inside. This one came from the derivative of the bottom. But it just happens to be the same exact thing. The derivative of 1 plus 1 over x, negative 1 over x squared, derivative of x to the negative 1, also negative 1 over x squared. All right, well, what happens here, and this won't always happen, so this is kind of an iconic example, but what happens here is that these exactly cancel out. Even though it's a messy fraction, it's being multiplied on the top and bottom, so these same exact things get canceled out. Now, if this was at all different, of course, if we had 2 over x squared, we should probably go through a proper way to simplify it, but this is no different than saying 2 over 2. You just cancel the 2's out and you're good. But because they exactly match, we can do that, and we're left with just doing the limit of this thing. 1 over 1 plus 1 over x. Now this looks terribly messy, but I can assure you it is not, because we only have an x here, and we know the limit as x goes to infinity of 1 over x. When we plug it in, it's 0. So we got 1 on the top over 1 plus 0 on the bottom, which is just 1, and 1 over 1 is 1. Right, now here's the slightly annoying part is you've done a lot of work, you feel like, okay, I got a number, I'm done. You're not 100% done yet. And the reason is you figured out the limit of the natural log of the original. So this is, I suppose right is, this is the limit as x goes to infinity of the natural log of the original. And it's just the natural log of y. So this is a whole bunch of equal signs. Keep in mind we want the limit as x goes to infinity of y. Well, how can we go from the natural log of y to y? It's actually not a bad step at all. What you can do is just take what you've known before. You can convert to exponential form, which is what I'm going to do. Or you can do e raised to each power, because e to the natural log of stuff cancels out. But I like to switch to exponential form. which means if you take your, let me actually kind of do it on the side here, the natural log of y equals 1, if you're solving this equation, your base, invisible base on the log is e, and you bring it over, and it becomes y equals e to the 1 power, which is e. Okay? So what we just actually figured out is that the limit as x goes to infinity of y, what we called our original thing, what we want to do the limit of, is e to the 1, which is e. All right, so just recap. We found this out. I just took the equation part without the limit and I converted it to exponential form because I wanted y by itself, and I figured y in this equation equals e. So that means the limit as x goes to infinity of y equals just e. And now keep in mind that is our answer because that is what we wanted. We want the limit as x goes to infinity of y, and that's exactly what we have. So this is our answer. Now it's extremely, extremely common when you have 1 to the infinity indeterminate form, when you convert and do all this stuff, that you get e's in your answer. You can get it with the other forms as well, 0 to the infinity, or not, sorry, 0 to the 0 or infinity to the 0, the other two indeterminate forms that are exponential, but it's pretty much unavoidable when you have 1 to the infinity. This is a very iconic example as well because this is really how infinity is defined. Or sorry, this is how e is defined. If you go back and want to Google or Wikipedia it or something, you can actually figure it out. The definition of e is this actual limit. Right, but I want to go ahead and summarize the two rules we did. Remember what I said before is that all the rules will follow similarly as far as strategy. So anytime you have one of these three, the first two may be able to do a different way, but you can do this way as well. What we do is we do the natural log of each side, simplify, and we also got that form where we, as we were going through, we got 0 over 0 times infinity, and we had to bring a part to the bottom. So, and bring part to bottom to make 0 over 0 or infinity over infinity. And that's pretty much the products one, is just this last part. Bring one part, and the easier one to do the derivative of, mind you, easier, to the bottom to make 0 over 0 or infinity over infinity. All right, now I'm still going to do a problem specific to this one right after this. But now that we have the strategy down, you'll see that it is the same strategy. Now I know there's a lot in this section, but really the difference one was very different than the strategy for the other two. And then the fraction one, we know that's just what we use for L'Hopital's rule anyway. So we don't have to do anything extra for that one. All right, so the last one I have here, it's the limit as x goes to infinity of x squared times e to the negative x. When we plug in infinity, the limit as x goes to infinity of x, of x squared is infinity. Whoops, a little messy there. And then the limit as x goes to infinity of e to the negative x, the exponent becomes negative infinity, so this is 0. So this is an indeterminate form, which means we must do L'Hopital's rule, but we cannot do it yet. We must convert to do L'Hopital's rule. Oh, and one thing I wanted to mention about this one is, as long as the inside limit's 1 here, it can be written a lot of different ways. You can have a rational function. You can have just one fraction where the limit is 1. You can have, really messy stuff like trig functions in there. As long as the limit of the inside's 1 and the exponent's infinity, you go through these steps. All right, but I just wanted to add that in real quickly. All right, so how are we going to convert it? Well, go ahead and rewrite it. Well, what we talked about before is we want to bring one part down. So either we're going to bring the x squared down or the e to the negative x down. And for this one, neither is terribly hard. If you bring one down, it really isn't going to make a big difference, but there is a better choice. Because when you bring it down, the exponent switches signs. Well, x squared is already a positive exponent, so I'm going to leave that one up. But I'm going to bring the e to the negative x down, because when I bring it down, it'll make the exponent switch signs to a positive x. I'm going to bring that one down, and that's just going to make it easier. All right, so we bring this one down. Now we do want to verify that we're in the correct form to do L'Hopital's rule, because you don't want to just start doing it yet. So we go ahead and plug in. And x squared, the limit as x goes to infinity is infinity over e to the x. Well, this exponent would be positive infinity, and that is infinity as well, which means we can do L'Hopital's rule now on this part. All right, so we're going to do L'Hopital's rule on this part. We have the limit as x goes to infinity of x squared over e to the x. We implement L'Hopital's rule, which means we do the derivative of the top. The derivative of x squared is 2x. Derivative of e to the x is itself. And can we simplify that? Nothing to simplify there, so let's go ahead and plug it in. And we still get infinity over infinity, right? The bottom's the same, so it's still infinity, and the top is 2x. And the limit as x goes to infinity of that is also infinity. Well, what's going to happen here is that no matter how many derivatives you do, this is going to stay e to the x. And as we do the derivatives on the top, the power of x is going to go down every time. And eventually it's going to be just a number. Luckily for this one, we only have to do one more derivative, but we need to do L'Hopital's rule one more time. So we got the limit as x goes to infinity of 2x over e to the x. Implement L'Hopital's rule. We got the limit as x goes to infinity. The derivative of 2x is 2. The derivative of e to the x is itself. And this one, when we do the limit, it's just 2 on the top, and e to the x limits as x goes to infinity is infinity. And a number over infinity is 0. So this is 0. Right. Now, a challenge type of question would be, what would I get if I had x to the 100 instead of x squared? Well, I can just go ahead and preview it real quickly for you, is that I do the power rule. Every time the power would go down by 1, and eventually it would go down to 0, and you'd get just a number here, like we have 2. Well, the bottom is still going to be infinity because it's always e to the x. So no matter how big this power is, if it's x to a power over e to the x, the limit as x goes to infinity is always 0. It's not something you need to memorize, but it is one of those types of examples that pattern recognition can help you. Even if it's just x to the 5th, that you're going to have to do L'Hopital's rule 5 times to bring the power down. But if you know x to a power over e to the x is always going to be 0, if you do the limit as x goes to infinity, then you don't have to do any extra work. So another kind of iconic example, but I wanted to do one where we just focus on the product indeterminate forms completely and not just inside another problem. And hopefully, you really get the strategies down. But plenty of practice coming up. So I will see you in the next video.